All right, so comments for the good of the order. I went just briefly through the titles. Some of them are just very brief titles. Some of them are whole theses in progress. And I just put as I said, my perfunctory comments. I think it's fine. We have 3 people do drilling. We have 3 people doing Iceland, people doing closed loop, said heat, thermodynamics. Taylor's doing EGS. I don't see him here, but a broad swath of things to do. Remember that if there are multiples, you'll be viewing multiples of these with your colleagues. So if there's, ultimately you'll all view all of these with the questions that you apply. So fine to go ahead. I guess Fatima's not here. Some of the one was introduction to geothermal energy or heat flow, so that might be difficult to make it an engaging presentation, although we've certainly talked about it here. But I guess it should be something that would pique the interest and keep the attention of you and your colleagues. So that's what you should aim for. It should be a tutorial presentation to educate your fellow peers about what's going on, and so that should be the kind of level that you should aim for. I haven't looked at the presentations that you're looking at in the class. Certainly the ones that were maybe done in 2019 are maybe the least refined, and the ones, so you'll have come to your own conclusions, I think, from the presentations that you've looked at as to whether they're good, bad, or indifferent. So obviously you should be aiming to trump those, for use of a better word. Okay, make them better. So to date we've talked about characteristics of phase changes. That's really what we were talking about, thermodynamics last time. I guess what we do know is if we look at this, then we've used this expression to represent heat rate out of the system as equal to the mass, very simple, mass flow rate, specific heat capacity, and the temperature change going from in to out. We know that in terms of a black box, what we're trying to do is put something in at a mass flow rate, and only if we can get it across the reservoir, has to come out at the same mass flow rate by continuity, can we expect to get a large volume of mass, which is really contained in the heat transfer fluid, typically water. Only if we can get that transmission through the reservoir do we have a viable reservoir. And secondly, only if we're able to add heat to that in the form of temperature, in going from inlet to outlet, do we also have a viable reservoir. So all 3 of these have to be high. This one's pretty well constrained. It's specific heat of whatever the fluid is. If it's water or CO2, they're around about the same order of magnitude, but these 2 other ones can differ. If we can't get water across it, we don't have a reservoir because we don't have enough mass of heated water coming out. And if it doesn't reside long enough, then it can't pick up temperature to be able to do that. So they're almost converse constructs, that we want it to be in the ground a long enough time to pick up heat, but we want it to be able to have a high flow-through rate. They're almost contradicting circumstances. So what we'll talk about now is how to be able to gauge exactly what the mass flow rates would be in terms of subsurface fluid flow in the reservoir. And so that's what we'll concentrate on. And I suppose the other important feature of what we've talked about already is that if we talk about pressure versus enthalpy, and we've had this cap diagram with trajectories of temperature coming down, and as you bring reservoir, we talked about the idea that we have individually different proportions dotted lines in our previous stuff, but this is basically the idea. So this would be 100% steam. This would be 100% liquid, and 50, 75, 25 as we go across here. And so given that potentially within our reservoir we have fluids traveling through that aren't just liquid or gas, but combinations of it, we need to worry about exactly what the kind of fluid that's flowing is. So we need to talk a little bit about that. So what we'll do today is we'll talk about multi-phase flow. In a rudimentary way. So Rhea, you'll have seen some of this before in these notes. So the question is, what rates can we travel, get fluids across systems? So for single phase flow, we use Darcy's law. And that essentially says that if you have a core across which you're flowing fluid at some rate, you can define the velocity at which the fluid comes out, the Darcy velocity, as a function of the gradient that's applied across it, the pressure gradient. And that's simply that the Darcy flow velocity, which is in length over time, is equal to something called the permeability divided by the viscosity of that fluid and the pressure gradient, which is driving it. So if we know that, we can always get the volumetric flow rate as being equal to the cross-sectional area of flow times the Darcy velocity. So we can always get this, and of course this, if you multiply it by density, gives you the mass flow rate, which is what we're interested in here. So if we are able to get that, then we can also get the heat rate if we're able to also solve the problem of defining how the temperature changes as you go from inlet to outlet, which is the key issue. But we don't always have that for a single fluid, because potentially we have within our reservoir, we have gas and liquid coexisting at any particular temperature and pressure. And so if that's the case, we have to be able to quantify how the fluids pass through our reservoir. And to do that, we merely use a construct whereby if you imagine being able to divide the flow system into, I guess it would be liquid and gas, or it could be, typically if it's liquid, if it's water, it's a wetting fluid, and if it's gas, then it's a non-wetting fluid, non-wetting. And those can individually flow in the system as velocity of a non-wetting fluid and the velocity of a wetting fluid. And together we can get the individual mass rates of these by doing this, if we know exactly what portions of the reservoir they occupy. And so that's going to be our task for today, is to understand multi-phase flow. So the system that we can imagine having is something like this, that we have flow paths that develop. It turns out that in this case, our non-wetting fluid would be green, I think, which would be air. And because of the capillary characteristics of that, the air will occupy the largest train, if you like, continuous train of pores through the system from one side to the other. and the wetting fluid will be relegated to the smaller, the bottom distribution of pore shape. If you take this and imagine it being centrifuge, so that you could move all the grains and the fluids that those grains contain into two different parts of the reservoir, so you have a non-wetting part and a wetting part, then what we can do is we can individually look, as we looked at the previous cartoon, flow just in the wetting phase and flow just in the non-wetting phase as separate. They have an interface between them. This interface will allow capillary behavior to operate, where surface tension of two fluids and the grains that contain those fluids separate them from each other. And capillary forces tend to be very strong, but away from this boundary, they don't have any relevance on the flow whatsoever. They just maintain this boundary. And so what we can do is we can think of it in terms of these two different components. To be able to get flows to occur from one side to the other for both fluids, they need to be connected. So for different levels of saturation, if we had it filled with water, the red fluid, but the air or vapor wasn't continuous across the system from left to right, then by definition, that can't flow. So any amount of flow that you get, this will be stranded and in place. The saturation will not change. And as we go across from one side to the other, there'll be no flow of the green fluid. If you inject green fluid into it, so the saturation of this green fluid changes so that it's now simply connected, then it will flow. And then once it's flowed, keeping on injecting more non-wetting fluid, in this case vapor, would allow it to be progressively higher saturations. I guess we need to talk about some definitions. I've used saturation, so we should probably define what saturation would be. So porosity would be the volume of voids divided by the total volume of the reservoir. So this would be the total volume of the reservoir. The volume of voids would be the void space. The saturation is equivalent to the volume of the fluid divided by the volume of the voids. So the saturations of the non-wetting is equal to the volume of the non-wetting fluid divided by the total void space. And the saturation of the wetting fluid, water, liquid in our case, is the volume of the wetting divided by the total volume of the voids. And so together, if we only have two fluids, since we only have the total volume of the voids and it has to be filled with both of these fluids, then the two saturations have to add to each other, add to one. So we can expect that this is the case. So if we want to be able to evaluate how flow occurs within the system, the easiest way for us to do it is to divide it into a portion which is saturated with the non-wetting, fluid 2 in this particular case, and the wetting. We can get the flow that is occurring, I guess I've switched these, no, okay. So this would be liquid, so in terms of our terminology, this would be liquid, and this would be vapor. And the velocity, Darcy velocity that comes out of that is equal to the permeability of material 1 divided by its viscosity and the pressure gradient that occurs across it. So the other way to think about this is that we have a pressure gradient driving flow, and that this flow comes out of here at some flow rate Q1, and this is dx. And we also have on top of this a flow where this, because these are parallel to each other, The pressures in the two fluids are not necessarily the same. They can be different, and we can define what's called capillary pressure as being equal to the pressure of the non-wetting fluid minus the pressure in the wetting fluid. They don't have to be the same because they're flowing in separate compartments, and it only matters on the interface what those are. But the gradients of pressure, dP dx, in both of the fluids happens to be the same for each of them. And the point being is that if we know the saturation of each of these fluids, we would expect that the area of fluid 2 is equal to the total area multiplied by the saturation of fluid 2. And likewise, the area of fluid 1 is equal to the total area of the system. So the total area would be this multiplied by the saturation of fluid 1. And so if we do that, then we can replace these components in here by multiplying this to get the volumetric flow of fluid 1 will be equal to the area of flow of fluid 1, the permeability, the viscosity, and the pressure gradient. But we know that we can define area 1 in terms of a total area multiplied by a saturation. So we can convert this to being a total area, which we like, multiplied by saturation of fluid 1, the permeability divided by the viscosity of fluid 1, and dP1 dx. This would be 1. The permeability is irrespective of the fluid that's being transited across it. It doesn't matter if it's vapor or liquid, so long as it's a Newtonian fluid. And so now this is the expression that will define the flow within our system in terms of Darcy's law, where merely what we need to do is we need to replace the permeability by a product between permeability and saturation, which gives us an effective permeability of the system. Likewise, for the second fluid, we can do exactly the same. It'll be equal to the area, the cross-sectional area of flow, which would be this red area here, which we don't really know. The permeability, viscosity of fluid 1, dP dx, fluid 1, 2. Make the substitution here, total area multiplied by the saturation of fluid 2 times permeability divided by viscosity, dP dx. And this is fluid 2. So the point is that instead of using permeability, all we need to do is use permeability to be able to scale with the relative area, cross-sectional area of flow. That's really all it's doing. And so if we were to, for instance, plot the saturation of those two fluids, saturation of fluid of the liquid, which is water, between 0 and 1, and plot that against the saturation of the liquid between 0 and 1, then when the saturation of liquid is 1, the saturation of liquid is 1 is here, and when it's 0, it's 0. And so this represents that fake curve, if you like. Likewise, if you do it for the saturation of the gas, saturation of the gas would be 1 to 0. So it's fully liquid saturated, there's no gas within the system. And if you draw the plot for this, then you get a straight line which defines this. So we're pre-multiplying these by a saturation, which is a multiplier on permeability. So we could think of this as being equal to what we'll refer to a relative permeability. So relative permeability varies between 1 and 0, and it just scales the basic areas as the saturations change, so that when all of the liquid is liquid 1, it's all red, and there's no green in the system, and that would be at this point here. And that means that if you take a section across here, the relative permeability to water would be something like to the liquid would be equal to 80%. And the relative permeability of the non-wetting fluid would be about 20%. They would scale directly between those numbers here because they're linear curves. So if we want to calculate exactly what the volumetric flow rates are of those components, which we need to be able to get this flow rate to get the mass flow rates, then we just need to be able to know what the individual saturations of those components are. And if we know what those saturations are, we can immediately get that volumetric flow rate. So there's nothing more than that. So we can define a relative permeability which acts on those in this form for the different fluids. And so I guess just to remind ourselves, fluid number 1 is our non-wetting fluid, the gas, and fluid number 2 is the wetting fluid. So that's not enough for our system. We also need to define it in terms of rates of flow into the system. So we can write Darcy's law in terms of both the pressure gradient, which is driving flow. This is pressure, and this is pressure. But there's actually an extra term that we need to include. It's not so important for what we're doing here. The reason we need that extra term is if you think about pressure changes as a function of elevation, then you know that if you're sitting in a swimming pool in a static fluid, then the pressure gradient is something like this. Pressure is equal to density of the fluid, gravity, and the elevation, or depth. This term here is the unit weight of the fluid, and if you define that in terms of this, then this is 1, and this gradient is the unit weight of the fluid. But if we know that this gradient, which is not 0, is sitting in a static fluid, it doesn't make any difference if we filled that swimming pool up with porous media, it would still not be flowing. So the velocity of this fluid should be 0. If the velocity of this fluid should be 0, that's certainly not honored if we only have this pressure gradient being, in this case, this would be in the z direction. This would be finite, it'd be non-zero. So it would suggest that since these coefficients are also non-zero, there'd be some flow rate in this particular direction. That's not the case. And so what you have to do is you have to substitute the magnitude for this unit weight. And I guess where that comes from is that we can define flow rate in terms of hydraulic conductivity and a head gradient, dH dx. This is how Darcy first defined it. This is a velocity. This is in meters per second, also velocity. And this, by definition, is dimensionless, length over length. And so if we split out those components, should have a minus sign here because it flows in the opposite direction, then this change with length is equal to the head, which is equal to the pressure over unit weight plus the elevation, at that particular point. And so really all it's saying is that if you have this Darcy stream tube and some kind of datum, that the flow that's occurring here, this is an elevation of 0.2. This is the elevation of the upstream 0.1. This is the pressure. This total is the head, and this pressure is 0. And so this pressure gradient in going from upstream to downstream rigorously is accommodated if Darcy's law is written in terms of a head, when you don't have to worry about this unit weight due to the swimming pool effect. But if you split this out in terms of this coefficient here, then you have to be able to accommodate that. So Q is equal to minus K, and it's dP dx 1 over unit weight plus dz dz. And so if you multiply both, if you multiply top and bottom with unit weight, then I guess you'd have to divide this through by here. Then you lose this term. You have this term, which is a unit weight multiplied by this. And we also know that we can link hydraulic conductivity, density of the fluid, gravity, is equal to permeability divided by viscosity as a standard result. The units of this link up. This is in meters squared. This is in Pascal seconds, SI. This is in meters per second. And this is in kilograms per meter cubed and meters per second squared. So you can play around with those dimensions, and you can prove to yourself that they're equivalent to each other on both sides of this curve, these just dimensions. And so K over rho G is immediately this term here. And so we can rewrite this as Q is equal to minus K over viscosity multiplied by dP dx plus the gradient of dz, it would be dx in this particular case, multiplied by unit weight. And so since we can write these equations in any orientation we like, horizontal or vertical, if we define our coordinate system, yeah, shout.
So you calculate the flow rate. Why aren't you considering the cross-section of them?
Because it's not a flow rate, it's a velocity. If you multiply, so Q, lowercase q is in meters a second. Volumetric flow rate is equal to Q times A, which is meters a second times meters squared. So it's definition, it's a velocity, it's a flux, what we call a flux. So if we write this for flow in the horizontal direction, in the x direction, so this is written in terms of x, this would be x, then the component of z in the x direction is 0 because they're orthogonal to each other. And so this term drops out, falls out. Don't need to worry about it. But if you're looking at flow occurring in the vertical direction, in other words, like this, then this now would be z, and this would also be z, and the component of z in the z direction is 1 to 1. And so this term would end up staying. So all by way of saying that this complicated expression here, where we have to include this term, is due to this, what I call the swimming pool effect. If you go down in a swimming pool, the pressure increases. There's a gradient in the z direction. That gradient in the z direction implies that the pressure gradient in the z direction would drive flow. But you know the swimming pool is static. It's static if it's liquid. If it's static if you dump a whole bunch of sand in there to go around the liquid, so it's sitting in the liquid. And so this term has to be in there to accommodate that. I'm not sure we need to know that in great detail in this class. The bottom line is that if we want to be able to calculate the volumetric flow rates of, how did we do it? Liquid 1, Q1 is equal to Q vapor, which is equal to cross-sectional area of our core, total area of our core, multiplied by the relative permeability for fluid 1, the viscosity for fluid 1, and the permeability, multiplied by dP dx. So let's forget everything we said before about this, just because it's not convenient for us to realize that. And let me do this. I'm going to be very fancy. And if we go back, and for Q2, which is the liquid, water, which is also equal to cross-sectional area, the relative permeability of the water at that particular saturation, the viscosity of that fluid, the permeability, and the pressure gradient in the x direction. So these two numbers are the same because the permeability is a function only of the material and not of the fluid that's saturating it. So we had this relationship, permeability, viscosity of the fluid equals hydraulic conductivity rho g. Hydraulic conductivity is a function of the fluid and the temperature of the fluid. In petroleum engineering and geothermal engineering, you tend to use behavior defined in terms of pressures and permeabilities because pressures change significantly as you go in depth. They change with elevation and also the temperature. And it's convenient for us to use a constant to represent the characteristics of the porous medium and have all the influence of the fluid that infiltrates it contained within the viscosity. In groundwater hydrology, tend to use hydraulic conductivity because it's measured at 20 degrees centigrade or 10 degrees centigrade and for water. So that hydraulic conductivity is a function of the fluid that's in it and its temperature, which defines its viscosity, and also these terms. So this is our formalism for this. Relative permeability would be different for each component, as we suggested here. It's very similar to this, but we'll talk about the fact that this is a very simplistic view of relative permeability. So we plotted saturation versus saturation and then called it relative permeability, which we can do, but we'll look for a slightly more sophisticated way of defining this. By definition, if these are linear trajectories, then these two relative permeabilities at any particular saturation of liquid and complementary saturation of gas, which would be 1 minus the liquid saturation. So Sg would be equal to 1 minus Sg, Sw, by definition. Then these will both add to 1. But that's not generally true, as we'll see in a moment. So that's a quick introduction to the flow of two fluids. And the final way of being able to evaluate that is in terms of this. Permeability is a function of the medium only, not the fluid, not the temperature, which is useful. Relative permeabilities, which may or may not add to 1. Not necessarily equal 1. Viscosities are the fluids that are flowing. This whole equation without the cross-sectional area would be what we would refer to as our flux, Q, which is a units of velocity, length over time, and multiplying that length over time by area gives us a volumetric flux. And if we multiply a volumetric flux times the density, that equals a mass rate of flow. And that's what we want if we want to get heat rate as being equal to mass rate of flow, specific heat, and whatever temperature that is traveling. And this is the kind of apparatus you might measure that in. So becoming a bit more sophisticated about this, our original relative permeability plots, saturation of the wetting fluid, saturating of the non-wetting fluid. So this would be vapor for us. So this would be liquid. And so what we had done before was we had plotted saturations relative to each other. And so they just went from one corner to this graph to the other. If you look at real magnitudes of these, however, it turns out that they are slightly different. They're slightly different for one reason, and that there's this kind of exclusion zone here. And so we know that if we draw a cartoon of what the saturation would be at this particular location on this axis, this would be 100% filled with the non-wetting fluid, with a few islands of water sitting in there. So this is vapor with a few islands of water surrounded by vapor. So in this configuration, the red fluid can't flow, and so you'd expect the red fluid to have a relative permeability of 0. So it would be here somewhere. So you'd expect within this zone that because it's not connected from left to right, that the permeability to the red fluid is 0. Likewise, since you can connect with the green fluid, then maybe it should be a bit less than 0, but a reasonable number to have for it would be to have it going across here at 100%. The reason it might not be 100% is that for the green fluid to flow from one side to the other, it has to go around these islands of red fluid, and so perhaps it should be depressed to some number rather than that. And so you might expect that it would look like this and then go here, maybe, except the reason it can't go here is that as you get towards this zone here, then all of a sudden the architecture of the flow is given by the non-wetting fluid, the vapor connecting both sides, sitting with liquid in the water connecting both sides, the vapor being patches within that, and therefore at this stage you'd think that the permeability to the red fluid might be here. Whoops. But because the red fluid has to flow around these islands of water, then perhaps that also should be reduced. And so perhaps a better representation of that might be this, because we know we can't get in this region here. And so not an unreasonable format for this figure could be, first of all, that this is the relative permeabilities, this is saturation of water, which is the liquid between 0 and 100, or decimal. This would be what we could have for this. This relative permeability would be 1 and 0. We know it can't be this because of the influence of these no-go areas. And so these no-go areas would be given by this. This is known as the irreducible saturation of the non-wetting fluid. This means that in this zone, it can't get 100% saturated with water because it can't get these bubbles of vapor out of it. And so it can't get in here properly. And so our compromise in dealing with that is to realize that these zones are off bounds, so to speak. And so if we did this, then a compromise would be to look at this. Here, there's no connection from one side to the other, so the permeability has 0. Here, there's a very good connection. It approximates 1. Maybe it should be less than that because we've got these islands it has to flow by. And between that, there's maybe a linear relationship between them. Likewise, if we look at the other phase, we recognize that it can't get in this zone. We recognize that it can't get in this zone at the other side. And to honor the fact that these should be 100% and 0% permeabilities in these two end-member zones, then it would look like this X-plot. It turns out that if we look at real data, then they start looking like this. And so the real data are that the permeability of the non-wetting fluid, don't want to do it as a straight line. You get the picture. That these actually are offset from these X curves. I guess the couple of features to maybe note, I don't want it to be that large anymore. I'm going to go back to my former size. And that is that this permeability here is higher than this permeability here. These individual relative permeabilities, if you add them together, so in other words, if you take this height here for this perm, and you take this height here for the non-wetting fluid, and add them together and plot them, you get this dashed locus. And this dashed locus clearly says that if you add the non-wetting and the wetting perms, then they're not equal to 1, because this isn't a straight line that goes across the top. And so this is a manifestation of the fact that, one, when you fill the pore space up with vapor and liquid, the non-wetting fluid tends to occupy the largest pore spaces and creates a continuous path across it in those large pore spaces. And so those large pore spaces have bigger diameters. And if you think about a pipe with a large diameter, it has a larger ability to transmit fluid at a faster velocity, faster volumetric flow rate than if you have ones with smaller diameters. And so the fact that the large pores saturate first with the non-wetting fluid is why this peak here is higher than this peak here, and that they don't. And in addition to that, they don't add to 1. So you see this. There are other quirks of behavior that if you look at the relative permeability as you put more vapor into the sample, it goes up one particular trajectory. But once it gets there, if it returns and you start saturating it with water again, so in other words, if you put more vapor into the system initially to go up this curve, and then once you get to a location, you push water back into the system to go into the opposite direction, you don't pass along the same curve. There's hysteresis on it. And one of the reasons for that hysteresis is if you think of a drop of liquid sitting on a windshield that is trying to roll down that windshield, then the tail of that windshield, of that drop, which has been smeared as it moves down, has already seen a wet surface, and it is pulled across it. The front of this raindrop, as it goes down here, is seeing a surface that has not been wetted with water for the first time. And so the contact angle between these varies depending on the history of whether it's been wetted before or not. And therefore, that's the essential mechanism by which the previous wetting conditions regulate the form of how it re-wets in the future. So this hysteresis is just a function of that. And so it makes it very complicated. And so you have these effects of wetting that affect this behavior. But for our intents and purposes in this class, we can think of this being as these heavy green line and the heavy red lines in these X curves that basically honor most of the features of this. We have these regions of irreducible saturation that we can't get in, where the permeabilities should be both 0 and 1 to the different fluids, and roughly between those we have some change. These are very hard experiments to run, so we don't know exactly, but taking this as an approximation is not a bad deal for us to do that. 1254. Okay, so how can we now use that? Well, what we can do is we can also develop models to represent that behavior. I made the point that the reason that this peak is higher than this peak is because it saturates the large diameter pore spaces within our system. So we can make capillary models that would represent the behavior of these systems. And the idea is to put together the porous medium. And if I draw this in perspective, then that would be that you could think of a whole series of tubes present within here, which would go from upstream to downstream in the system. And you could choose these tubes so that they would honor the characteristics of the porous medium. So they'd have some diameter that would represent the individual pore throat diameters as you go through the system. And it would also have some kind of a porosity, which we already defined as being equal to the volume of voids divided by the total volume. So the total volume, I guess, would be equal to this cross-sectional area here, which is our Darcy area, and this would be some length. Where's that? So the total volume would be equal to total area times this length. In other words, just the blue cross-section multiplied by length. But the porosity is given by the volume of voids, and the volume of voids is conditioned by whatever diameter that we choose for this. And so this is motivated by the fact that if we look at characteristics of permeability, we've defined Darcy's law in terms of this flux, which is permeability, viscosity, change in pressure and length. It turns out that this permeability is pretty close to, it's a unit of length squared, meter squared, and it's pretty close to being the pore diameter to the power 2. So it scales with the pore diameter. And so what we could use is develop relationships which define the permeability of this porous medium as a function of its capillary characteristics, so-called capillary relations for permeability. And it's pretty straightforward. The idea is this. This is the diagram I just drew you. These are the individual capillaries. This is the length of flow. This is the cross-sectional area of the whole sample, the core, if you like. And what we want to do is be able to define how quickly fluid flows through here. And we'll do it by getting the total flow across this boundary as equal to the sum of all the individual flows that occur in these pipes, these capillary pipes. And so to do that, we need a fundamental solution that defines what the flow, average flow velocity in a pipe is. And it turns out to be this expression here. It's driven by the pressure gradient that is applied, Tp, over dx. So this is what's driving flow. This is the viscosity of the fluid that's flowing in each of these tubes, and this is the diameter of each of these tubes that we have here. And so this just comes from solving for flow within a pipe. If you look at a cross-section across a pipe and look at the flow velocity within that pipe, if you solve the Navier-Stokes equations, which are solving for, that's not bad, it's done kind of what I wanted. Oh, that's pretty good. So if you solve for velocity of flow, then the maximum flow velocity is in the middle of this pipe. The zero flow velocity is at side. If you solve the differential equations for momentum and mass conservation in this geometry, you get this expression. This expression says that the velocity as you go across this pipe is anchored to zero velocity at the walls, where it's a no-slip condition, and a maximum velocity at the middle, so it's a parabola. And if you take this distribution and you get that area under that curve and convert it to an average velocity, what we're calling u, is this area here is exactly equal to this area here. So this is an average velocity that's represented. So I guess you could also do it by taking the total volume coming out of this round tube with time, dividing by the total area of this round tube, would give you the average velocity. So if we get the volumetric flow rate per tube, that's going to be equal to this expression here, which is the velocity. If we want to get the volumetric flow rate, we multiply so this here is the area, pi d squared upon 4. And so this is the total amount coming out of a single tube. We need to know how many tubes there are. We can't choose that arbitrarily because we need the number of tubes which are void space to honor the fact that we have a certain porosity in this system. And so what we need to do now is define the porosity as the volume of voids divided by the total volume. The volume of voids is going to be the area of the voids, which would be all of these individual cross-sectional areas of the red, AV, multiplied by the length, which would be the volume. And the total volume of the cube would be this face multiplied by the length of flow. So we can get each of those. So the area of each void is pi d squared upon 4. If we multiply it by the number of those tubes we have, which we'll call I, that's the total area. And if we multiply an area by the length, that gives us the volume. That's these holes in the Swiss cheese that we have here. Conversely, the total area is the area of this front, which is dy dz, and multiplied by the length over which this flow occurs. So it's the total volume of this cube. And if we substitute those together, we get the total volume, which is equal to pi d squared upon 4. The flow, volumetric flow within each tube, or the velocity within each tube multiplied by area gives the volumetric flow rate. So this here is Qi. And the total number of tubes is just this term, where we know everything else. We know all the dimensions of our system. We know the diameter of our pipes. And we know the porosity that we're trying to honor. So we just rearrange this in terms of the number of tubes. And if we do that, we get this expression here with porosity. And if we work those out, then we realize that any term that we get is a volumetric flow rate, which is an area, a permeability, viscosity, and a pressure gradient. So we just need to split up this expression in terms of those components. We get rid of the areas, top and bottom, and we're left just with this expression here. And so if we want to divide that between the different components, the area is given by the cross-sectional area at the front, dz by dy. The permeability divided by the viscosity are the terms that remain here. And if we take the pressure gradient out, we're left with that. So this contains the volumetric, the viscosity. So by definition, for us, the term which represents the permeability would be this. And so we have a capillary model which just says that if we take the diameter of our pore spaces multiplied by porosity and divide by 32, we get a magnitude for permeability. And so sometimes, not always, will we want to get the permeability from the diameter, but one way in which we might use this is to rearrange it and use it to rewrite it in terms of the diameter squared is equal to 32 times permeability times porosity. And if we have that, then we get rid of this square root. This is just square root. And so now, if we have a measurement in our system of the permeability, if we know what the porosity of our core is, it gives us a capillary diameter. And the reason for that being useful is if we want to calculate what the capillary characteristics, the resistance to invading a porous medium, it's a function of the magnitude of the diameter of the capillaries. So we can use that. The other thing that we can do is that our particular geometry has represented the behavior where we have all these capillaries within this cube all aligned in one direction. If alternatively we draw the cube where we have the capillaries arranged in the x direction, as we did previously, right? So we had this face with these capillaries extending back into this face like this, which represents this. But if we also have capillaries going out from this face, which would have to come across from the other side, if we calculated what the permeability of this would be, we'd get that the permeability would be equal to porosity d squared divided by 64. And that is because we've divided the porosity between the capillaries which are flowing in the x direction and also the capillaries that are flowing in this particular case, the y direction, in this direction. And so that means that that volume is distributed in those two sets, but we're only getting flow out of one of them. And so it cuts the permeability in half. Likewise, if we then go back in and finally we take capillaries on the top, which are going through it, which is what this diagram here is trying to show, then this one would be not 32, not 64, but 96, for that reason. And so we have to decide which one of these to use. Turns out that since permeability is so sensitive to the diameter, this changes it by a factor of 3 in going from these, but a very small change in diameters makes a big, big change in permeability. So even though it seems it's a bit arbitrary that we choose these, it doesn't make a very big effect overall. And I think the final thing I wanted to say today is, well, we've covered this already, we've used it. This fundamental relationship allows us to link permeabilities to hydraulic conductivities. So the units that are the currency of petroleum engineers and geothermal engineers in permeability versus that which is of soil scientists and hydrologists, groundwater hydrologists. This is a function of the fluid that's flowing and the temperature you find yourself at. This is a function only of the rock that it's going through. A permeability of 10 to the minus 18 meters squared for a sandstone is the same if it's flowing water or vapor or gasoline. It doesn't matter, as long as they're Newtonian fluids. The influence on permeability in the flow equations for us is accommodated in the choice of the viscosity for the different fluids that they're flowing and the temperature at which they're flowing. And if we want to get a volumetric flow rate that represents our system which has a relative permeability, then we have to use a relative permeability that represents that behavior. So this is our fundamental relationship. Permeability doesn't change. It's only a function of the rock. Viscosity changes with whatever the fluid is. Cross-sectional area of our pipe is a total cross-sectional area, just to summarize. So this is area. It happens to be divided between two areas for the two different fluids. But that, for us, is manifest in the fact that we have a saturation of a fluid I, and we have a saturation of a fluid J, whatever they are. And so that is what's represented here. The saturation of water or gas changes. That defines what this relative permeability is. That gives us this location on this graph for a given saturation as we go up here, that we get a magnitude for the wetting fluid and the non-wetting fluid. And so for any given fluid, we can calculate the mass flux from this. Total area of the core, total permeability, viscosity of the flowing fluid, the pressure gradient of that flowing fluid, which happens to be the same for both fluids really, for what we said before, and the relative permeability, which is defined by this particular saturation. And that's about it. And so, as we said before, the end result of this is that we want to calculate heat rate. It's equal to mass flow rate times the fluid times how much heat we pick up. This mass flow rate is equal to volumetric flow rate multiplied by the density of that fluid. And potentially we have two components that we would add together to be able to gather the total component. So both the liquid and the vapor would have different temperatures potentially and different mass flow rates, but together, by adding those together, we could get the total amounts. And I think that's all I'll say today for now. Okay. Questions?